Talk of the day. Hope you guys having fun up to now. And then, well, now we have our pleasure to present Luca Apadula for the next talk, right? And he's going to talk a little bit about quantum reference frames, right?
Sure.
And it seems fun. I mean, it is fun. So
Hopefully.
please, go on.
Okay. Hi, everyone. And first of all, I would like to thank the organizer for inviting me here in this beautiful event and to give me the possibility to talk about one of my last work that I've done in collaboration with some of my colleagues. No, this one, yeah. Victoria Cabel, Anne-Catherine Delannette, Carlo Cepollaro, which is a speaker of this workshop, is going to talk tomorrow about quantum reference frame and equivalence principle. And then we have Enrique Gomez, Jeremy Butterfield, and Czeslaw Bruckner, which is our supervisor. Okay, so I'm going to discuss a physical scenario emerging from quantum reference frame formalism. And I'm going to basically explore the conceptual consequences of this. This physical regime is something that we've seen so many times during these talks. It's basically the fil rouge connecting most of the talks that we've seen so far. And yes, based on quantum reference frame, okay, I need lots of time to introduce quantum reference frame, so I will try to give you like a brief and intuitive introduction, okay, of this formalism. So, basically, whenever, I think that everyone here in this room agrees on the fact that physics is relational. Every meaningful relational statement, a meaningful physical statement is a relational one, so providing a quantum state, a set of algebra of observables, defining a measurement apparatus. All these things are always defined with respect to a physical point of view, physical object, which is called, indeed, reference frame. So the fundamental step is the following. Now we extend the quantum domain of those objects we want to use as reference frames. And so that we are able to phrase a question like the following one, like how would a quantum particle, which is, for example, in a superposition of space location, would perceive the physical world, okay? So let's try to focus on this physical scenario. We have our guy sitting on the planet Earth. So the planet Earth is basically the reference survey we are considering right now. And the guy is describing the state of a satellite, which is in a superposition of location minus a and plus a with respect to the Earth, which is the origin of the spatial reference frame. And then the probe system, which is this atom, this atom, at 0 position. Okay. So now, one caveat, if you check the state, the quantum state, here we wrote down the state of the reference frame, which is factorized from the rest of the physical scenario. But keep in mind that this is not really quantum degrees of freedom in the sense that we cannot actually measure it, because if this was possible, this would have meant that actually we are taking the reference of another physical entity that would have given us the possibility to measure the Earth. So it's basically a parameter bringing the information of where the origin of the spatial reference frame is set. And so now I want to jump on the satellite. I would like to perceive how I will describe physics from that perspective. Okay, now we can discuss about the transformation, no, to be applied. And I won't show you now the full derivation, but like intuitively we can say, okay, now I need a translation that would act properly on each branch of the state with a specific translation. So quantum controlled translation. Okay, since indeed do not have time to derive everything, we can ask our Deus Ex Machina to provide us the right transformation. So this is basically, okay, I can briefly comment about that. You can see there's a translation which is controlled by the state of the Earth and the satellite. So if we act on this state, the 0 fix x to 0, we have just a minus x prime, so entangled control of the satellite, and then indeed x prime, which will be the parameter which will program the transformation acting on the probe system. Okay, so let's act with this transformation. This is what we get basically. So now the guy is sitting on the satellite, and what we are perceiving is the following. The state of the satellite now is factorized out as the Earth was before, and now we are perceiving an entangled state of the Earth, an atom and in a branch at position -a, and the other at position +a, okay? So what do we see now? Okay, we have this physical regime basically, no? If we accept the validity of such kind of transformation, we have a superposition of massive objects, okay? And then we can ask, okay, but now, what does it really mean to have a superposition of space-time location? Also, how can we give an operational interpretation of such kind of physical regime? And also, if we make an extra step and then we retain linearity of quantum mechanics, then we have to admit that we are in presence of a superposition of gravitational field, okay? And now, what I'm going to introduce is basically a theoretical framework in which we are able to describe any possible quantum gravity theory. We are not really interested in sorting out the fundamental one. We are basically interested in any possible quantum gravity theory as long as it presents this kind of physical regime, so superposition of states picked around semi-classical metric, okay? And now, okay, we are going to be able, we will try to see the conceptual consequences of this kind of physical regime. Okay, and now let's start with the presentation of this theoretical framework. Okay, now we are going to represent a generic theory labeled by capital Phi, and the symmetry endowed with a symmetry group identified by G. Okay, and here we have the space of solution, or models or configuration, I will use these terms interchangeably, which are sorted out in orbits under the action of the symmetry group. So 2 points on one orbit basically are always connected by the action of one symmetry transformation, so they represent all the physically indistinguishable configuration of our theory. And instead, I mean, 2 different orbits identify 2 physical distinguishable solutions of our theory. And now, another ingredient, which is going to be very important in a few minutes, is the notion of a reference frame, in a sense. Okay, here it's called as section, is a map, which basically enables us to pick up specific representative for each orbit. Okay, now, I mean, there are some caveats. It's not always possible to identify a section which is global, but for the sake of our talk, of this talk, let's consider this global. So it basically pick up a representative. It means it fixes a configuration, a gauge for each orbit, and this basically translates in finding a complete and complex enough reference frame that would fix the gauge redundancy, no? In order to make a connection with the example we've just seen, a possible action would be take the origin of the spatial reference frame, so the guy, at the position of the satellite, basically, okay? This is a choice of a section. And now, this last little tool, which enable us to make a comparison of such configuration. Okay, we have this configuration and provide you like 2 points on two distinct orbits. Okay, if they are in two distinct orbits, we already know that they are basically physically distinguishable or different, but I can ask you that I want you to make a comparison of the two. And basically, this is made by identifying first a section. So we pick up a section that in this case is going to be, for example, make a connection indeed with this example, the position of the satellite. So these two configurations now, they will be aligned by the action of one specific symmetry transformation, one translation, okay? In this case will be a translation of D, in this case of D prime, in order to be aligned on the section that we picked up. And then you can build up this map, which is a suitable composition of these two transformations. And for example, now if you apply this counterpart relation on phi, what you get is that, okay, there's this kind of movement of the point of this configuration is brought down and then again up at the same gauge configuration the first. So now that basically they are aligned with respect to the reference frame that you have chosen, you can make a comparison. You can see in which physical elements they actually differ. Okay, and now we are going towards the meat of the talk, because now we'll try to phrase quantum reference frames for general relativistic theories within this theoretical framework. Okay. So, okay, now we're discussing general relativistic models. So a configuration is given by this set of objects, some manifold, metric tensor, and whatever we are describing, so matter fields, and the symmetry group is going to be the diffeomorphism group of our manifold. Okay, so far there is no basically quantum ingredient, no? So now the quantumness enters in the game in this way. Now, if I provide you, like in this slide, 2 points on 2 different orbits, this is not just a mere list of configurations, but it's going to be the real, somehow, physical state of our model, of our theory. So it's going to be basically a quantum superposition of these 2 configurations, okay? And now there's the problem on how to describe physical reference frames, a quantum reference frame, as we are in a quantum regime. So in order to do so, we choose a suitable set of scalar fields, okay, and by means of that, we can basically provide an operational coordinatization of these 2 manifolds. There are a couple of caveats, and maybe we can discuss about very briefly about the choice of these reference fields. There are 3 cases. The first, basically, it's completely unphysical. It's not suitable for our goals, because if we take in account fields which are completely idealized, which means they are not dynamical, they don't fill the metric. It means that if you choose, it means that they are basically coordinates, and they cannot fix the gauge redundancy. So this is basically useless. Then there's the case of dynamical fields, which means that they fill the metric, but they do not backreact, which is basically what we are going to take in account. And then we can always take the complete and somehow more realistic case of dynamical fields, which also have a backreaction on the metric, but this is going to make the situation way more complicated, and for the sake of our goals, it's not bringing any insightful things. So we can proceed with the second option. And now, okay, I want to use k-fields, okay, to coordinatize this physical configuration, to use the k-fields as a reference frame, okay? So basically what we do, we use these k-fields to label points, to give an operational labeling of points, and now, most importantly, since we have this superposition of manifolds, to give a notion of identification of pair of points, which means through this map, which is called the comparison map, okay, which is basically composition of the k-fields in the two branches, I obtain a map which is able to indeed map one point from one manifold through the physical values of our quantum coordinates to a point in the second manifold. What does it mean? That once I make this identification, it means that these 2 points are operational in the sense that they correspond to the same physical values of these quantum coordinates or quantum reference frames. Okay? Now, I will try to, using this tool, to phrase, okay, what taking the perspective about quantum reference frames means, and also how I can change the perspective, how can I can change the scalar fields that I use to make this coordinatization. So we start from this case. Okay, now I'm using k-fields. It means that I'm sitting on the k-fields. So what does it mean? It means that we have chosen a sigma, a section, which has identified a specific gauge configuration for the k-fields in both branches, okay, which is chi star now. So chi star is the same, can be factorized out as the state of the Earth in the previous example was, okay? And so the physical content is at the right part, okay, of this state, and this now serves simply as coordinates, okay? We're not gonna be able to measure the k-fields, no? But it's exactly what we use to coordinatize the rest of the physics. And now, in this configuration, the models are aligned with the sigma if we are sitting on top of them, no? And the comparison map by construction is simply the identity because chi2 and chi1 are the same. And now basically, I want to change my reference frame. I want to jump on top of another set of quantum coordinates, of quantum fields, scalar fields, chi tilde fields, and then again. So first thing, you have to choose an arbitrary section which fixes the same gauge configuration for the chi tilde fields in both branches, okay? And then, once you have it, you can identify what the diffeomorphism, I mean, which kind of diffeomorphism you have to apply to each orbit in order to align the configurations to the section, okay? So it means, basically, to make a connection with the example we've seen before, we have to identify the right quantum control diffeomorphism, as we were identified before, this quantum control translation for the first example, which will do this, okay? We'll apply accordingly the D1 diffeomorphism and D2 diffeomorphism in the two branches, in the two orbits corresponding. And then what we see is that, okay, once we are aligned, so once now we are able to write down such kind of quantum state, because now indeed chi tilde star is the same in both branches, so I factorized, the comparison map built with the new quantum coordinates is now the identity. The old one So the one built up with the old K fields, which undergoes this quantum control transformation, is not going to be the identity anymore. And this is a fundamental ingredient for what comes later. Okay, and so, okay, now we have basically all the ingredients to see what the physical implications are, no, of this physical panorama, indeed. So, let's see, now basically we are able to pose the question, what does it mean to have superposition of space-time location now that we are using, okay, quantum coordinate system, now that we have basically a tool to provide an operational meaningful answer to this. Okay, and yeah, the essence lies in basically in the use of the comparison map, I would say. Because now we have this comparison map, it means that we are sitting on top of the K fields, and we have this identification, so we identify P and Q, okay, as we've done before. So these 2 points correspond to the same quantum coordinates. Now, we change the reference frame, we applied whatever we see in the previous slide, so the quantum control transformation, and now we build up the new comparison map, the C tilde key. And we make this identification. We take the, it's not P anymore because P underwent the action of diffeomorphism, so it's going to be the image under the D1. So D1P is mapped not anymore in the point that would have been mapped by the previous quantum coordinates, quantum reference frame, but is basically mapped in a different point. So what can we say at this point? That identification of points depends on the reference frame that we are taking into account, okay, by which we are making the identification, okay? It's not absolute in a sense. And okay, here there are a couple of concrete, yes, maybe this one is not so concrete, but toy models, let's say, in order to make a different representation of what I just show you, basically. So here we have these K fields, which basically coordinatize physics through colors, red, green, and blue. We can see that according to this physical scaffolding, P and Q correspond to the same physical configuration of K fields. And now we change, and now we find, we pick up different scalar fields, identifying temperature, pressure, and luminosity, for example. And what we see that the identification is now different, okay? So D1P now is mapped in another point, in another physical configuration, okay? So, and this can be seen also in this other case, which is probably phrased more in a general relativistic fashion. We can choose as quantum coordinates, so scalar that we computed from Riemannian and Weil and Ricci tensor, and basically repeat the same analysis. The point is always the same, no? It depends on the quantum coordinates that we are taking into account, okay? So the localization of points, the identification of points is frame-dependent notion, okay? And now we can say something about space-time localization of physical events, no? As before, now as an event we consider the crossing point of 2 word lines. So we are sitting again in the field chi, and we have the identification of P and Q as before, and we have that the event crossing point of these board lines happen in the same coordinate provided by the key field. So basically they happen in the point, in one branch in the point that I called before P, and the second branch in the point Q, okay? So it means that these physical events is space-time localized with respect to these quantum coordinates. But then what we have is that we can again change the reference frame, and what we get is instead that the event in one branch is mapped actually into another physical configuration which doesn't correspond with the same event, okay? So the two events, they happen at different coordinates according to the chi tilde fields, okay? So space-time localization of events, now physical events, is frame-dependent notion, okay, has not absolute meaning. Right, and now we can phrase this result in this catchy way, this quantum Hall argument, because now I don't want to phrase again the Hall argument per se, because I think that everyone is quite aware about what Hall argument is, but it's basically the argument that that Einstein raised in order to show that there's no substantivalism of space-time anymore, in the sense that points of the manifold has no absolute meaning. This is a direct consequence of general covariance. So if I take a matter field, psi of x is not a relational statement, it's not psi with respect to a physical point of view of x, but x is just a fiducial, it's just a label, okay? And now that we have this scenario in which we have superposition of manifolds, we have a second, we've seen that it's very important to make this identification of points, okay, using physical fields. So one could think, okay, now I provide identification through physical fields, that this identification is actually absolute, has an absolute meaning, but it doesn't happen. This depends, as a relative meaning, because depends, again, on the specific choice of quantum coordinates that I made. Okay, the same thing can be basically phrased for observables, same thing as basically what I previously shown you for localization of events. So now, if we have, how much time do I still?
13 minutes.
Okay, there's plenty of time, I guess. Okay, so before we talked about localization of events, okay? Similar thing can be phrased for general observables, okay? So, again, we pick up a specific observable, O1 and O2 for the two branches. We have our identification comparison map, so we are using chi fields again as a reference frame, and we make the identification again of point P and Q. So if the observable has the same value on these 2 points, it means that is definite with respect to this reference frame, which is the counterpart of being space-time localized. Now, what happens if we change again the reference frame, we use the quantum coordinates chi tilde, it could happen that the identification now is different, so D1P in the image via the identification map C chi tilde, and now if the observable has 2 different values, okay, on these 2 identified points, it means that is undefinite, basically is in a superposition, which is the counterpart of being delocalized in space-time, okay? So also being definite or in a superposition, it is a frame-dependent notion, okay? And now, to conclude, I will just to make, to underline this little criticism that was raised recently. Whenever you have the possibility of enlarging the symmetry group by taking a quantum-controlled transformation, okay? So, as you can see, we have, can take in account this experiment that we've seen so many times during this workshop, superposition of trajectories and then recombination in interferometer, okay? So they raised these, in this work, Adlam et al., they raised these criticisms saying, okay, if you have this possibility to perform such kind of transformation, then you might actually get in two branches now of the superposition two different experimental outcomes. Okay, so what is actually happening? Okay, this is the configuration, and this is exactly what they claim, no? We change the quantum reference frame. Now we describe such kind of physical setup, physical configuration. So we have a superposition of the points in which the masses basically recombine, and they claim that these two branches, they might bring to a different phase. Okay, this is basically untrue, because the phase difference just depends on relational quantities, okay? Relational quantities that you build up using the relational distance of the interferometer and the particles that they are recombining there. And so basically what does it mean? That acting with a quantum control transformation doesn't affect anything that was already preserved at the classical level, and the only thing is that you will have a delocalization, a space-time delocalization of the meeting points, okay? And there are also some other ways to phrase it. I mean, the difference in phase is what you get by computing the circuitous integral of the engaged potential, depending on which kind of symmetry we are considering here. And we know that this Wilson loop is basically gauge invariant, okay? So that's it, okay? This was the last thing that I wanted to raise. And so what we've seen, I briefly discuss a quantum reference frame situation, okay? And then I try to phrase this quantum reference frame scenario in this very simple from theoretical framework, in which is basically possible, has been possible to ask the questions before, not to understand all the conceptual consequences of those physical regimes. And basically what we understood is the localization of events, okay? Given this operational understanding, operational characterization of localization is not absolute, but is frame dependent. As it is frame dependent, the notion of being definite or in a superposition. And with this, I conclude my talk, presentation.
Thanks, Luca, for the great talk. And questions, guys? You can see.
So how do you deal with the case, or what do you do in a situation where your coordinate fields have some repeating coincident values, you know, some...
Yes, of course, yeah, okay, I haven't discussed that, no? Because you need them to be inhomogeneous enough in order to coordinatize this, at least the bunch of space-time that you are interested in. And then, of course, if you cannot find them, then it means that this is not, I mean, you can coordinatize really just a chunk of space-time, basically. It's not so much extended. And yeah, that's it. So, I mean, we haven't really addressed these specific problems, but the limitation is that. I mean, the reference frame is not powerful enough. You can coordinatize just like a partial frame of your physical configuration. Yeah.
Well, thank you very much, Luca, for this amazing talk.
Thank you.
And this framework, it reminds me a lot of fiber bundle theory.
Yeah, yeah.
But something that got me a little bit uneasy was in this discussion about the space of space-times and this discussion for the specific case of general relativity, in which I'm not sure if I follow everything. Are you considering, for example, in all of that space in which you take a section, space-times with different structures, so that are not equivalent by diffeomorphisms? Because if so,
yes. I think so. Let's go back in the first. Okay, yeah. So, I mean, the two orbits identify two physically, I said physically indistinguishable, so it means that there is no diffeomorphism connecting any of these, any couple of the points that you pick up in one and the other. So basically, the full physical configuration is diffeomorphism equivalent. There's no diffeomorphism that will connect them. Yes, this for sure. But I don't know if you're talking about, you're saying something just related to the metric tensor now?
No,
or?
not quite. What I'm finding a little bit uneasy is that in this case, isn't the symmetry group different for each orbit?
No. The symmetry group is not different from each orbit. The symmetry group is the symmetry group of the theory, and this is the set of all possible configuration of the theory. But the symmetry group is still a diffeomorphism group of the manifold.
Yes,
I
but
would say.
wouldn't for example, for in a two-dimensional case, for simplicity, wouldn't the diffeomorphism group of a sphere be different from that of a torus, and both of those be contemplated in this full space?
Okay, but in that case, I mean, let me think. I mean, it could totally be that maybe here you have a manifold or like a metric tensor, which is basically describing a sphere. Here at torus, this could happen. But yeah, I mean, I don't know. I would have naively, I would say that the diffeomorphism group. I mean, the diffeomorphism group in both cases will not change the topology of this structure. So I don't know. I don't see how taking a sphere or taking a torus, this would limit your symmetry group.
Okay.
I don't, but we can maybe discuss it later.
Okay, thank you.
Okay.
I think this is sort of a continuation of the previous question with a concrete example, because I'm glad you mentioned Wilson loop. You know that this is a Wilson loop.
Mm-hmm.
So it's a Wilson loop in space, which sort of, if it was an infinitesimal Wilson loop, it transforms as a 4-vector, which is time pointing.
Mm-hmm.
Now, I mean, you mentioned the interference experiment, so let's take the BMV type experiment, which is two Wilson loops talking to each other. In the lab frame, you have Minkowski, plus a virtual graviton. And in Minkowski space, you count the in Minkowski space, you conserve energy and momentum. In the frame co-moving with the particles which are in superposition, this is of course a superposition of two frames, neither of which conserve energy and momentum. So the quantum operators for energy and momentum are not, you know, the Hilbert space is not a representation of energy and momentum in those frames because they're non-inertial frames. And if you have general covariance between the two reference frames, you should have a sort of four-vector of operators that transforms covariantly between these frames. I'm not sure in which the conservation laws are totally different. I'm not sure this is sort of possible if this is sort of if this is unitary. I mean, of course, this is sort of an infinite dimensional space, but it just looks, you know, it just looks weird.
I don't see why this wouldn't be possible. Okay.
Because the conservation laws are completely different.
Yeah, I mean, okay, I haven't talked about conservation. Yeah, I mean, this is another thing. I mean, I haven't talked about conserved quantities and variance. This is basically an extension of the symmetry group, basically. But yeah, this kind of, okay, maybe I haven't get completely what you raised now, but so I don't know. I'm not able to to give you an exhaustive question, so answer. So but.
I think it's a crucial point because the question is, if the BMV result is the canonical quantum mechanics one, will it be also generally covariant? I would bet no, you know, and vice versa.
Okay. Okay.
So about the BMV point that you responded, you show the part of a paper signed. So
yes.
I don't understand because at the end you don't have you have to have the phase.
Yes.
And that's not a problem for you because things are relative to the end and the beginning point. My question is, if in the end you end up with like this phase between reference frames, does it mean that when you end your experiments, you have two different reference frames that will give the same experimental results? They are equivalent, but I didn't understand your answer to the problem.
Okay, the point is that they say, look, I mean, you start from this configuration, no? From one quantum reference frame. Then you change quantum reference frame. And this quantum reference frame, probably the reference that you were using here was maybe in a superposition, was indefinite. Then, according to that point of view, now the point of coincidence, meeting point in the interferometer is delocalized according to that. But this doesn't change the relational quantities, which are those that you have to take in account in order to compute the difference in phase. And there's no...
Okay. So but this comes back to the fact, to the substantialism thing, because if space-time were a thing, it was something like more realistic, this would be a real problem, because you have two space-times kind of not recombining. But if everything is relational, so
yes.
That's not a problem.
Yeah, right.
That's it.
Yes, yes, okay. Right.
So
yeah. No. It's quantum relationalism.
Yeah, if I'm space-time realist, this
yes,
would be a serious problem, but it's not.
No, it's not at the
relational.
very beginning. Yes.
One last question, guys. No. Okay, so let's thank the speaker again. And I guess